Hello, everyone. I'm Billy Younger. I'm just here to show you how to solve a banked incline problem. So basically, we're planning on banking a curve so that a car could go around it with a frictionless condition. So, in other words, only the normal force acting on the vehicle will be enough to, or will be sufficient to give it the centripetal acceleration it needs to make it around the curve. So it's basically like a non-friction problem where you're solving for, with no friction force, what speed, given a velocity v and a radius of curvature r for the curve, what angle should you bank the curve so that the vehicle doesn't need friction to keep from sliding up the incline. So let's turn on my document cam where I've got a sketch of the thing already put up, and we'll create a free body diagram. So here you can see this is the idea of the sketch. The angle theta is the angle above the horizon. We're banking it. We're just going to say an angle theta, and that's what we're wanting to solve for. We're going to say the vehicle has a mass m. It's traveling at a velocity v, and it is traveling at a velocity v, and the curve has a radius of curvature r. So we're going to assume we know these three quantities, and there's no friction force acting on it. So what I'm going to do is I'm going to take this over here, which is my positive y-axis, and this over here, which is my positive x-axis, and I'm going to use this to create a free body diagram so that we can actually solve the problem. So first thing I want to do is I want to represent the vehicle by a dot, and then I'm going to put a mass m right here next to it just to show that this object has a mass m. I'm going to draw a force, the normal force that the curve is applying. I'm going to try to draw it perpendicular to the actual curve, which I'm representing by that little blank one. Notice I did draw this in neither orange nor green, so this is a force that hasn't yet been decomposed into X and Y components, so it's off color. Now, the other force acting on it will be the object's weight, which is the object's attraction to the Earth, or Earth's attraction to it. So it's pointing in the negative Y direction, and its quantity is W, which is equal to the object's mass times G. Notice that's pointing in the negative Y direction, so I went ahead and made it orange. To counteract that, of course, we have to break these components up, or this vector up into its components. So I imagine a right triangle right here, and I'd see the X component is clearly positive, and the Y component is clearly positive as well. So those are my two components of F normal. Now I just got to figure out the geometry of the situation. We see from here that the angle is actually theta is right here. That means this angle right here is also theta. But since this is 90 degrees, then this angle must be 90 minus theta. So I could say that this angle up here is theta, or I could say that this angle down here is theta. Either one works just fine. Okay. So from that, you determine that this force right here is F normal cosine theta, and this force right here is F normal sine theta. Now all I got to do is apply Newton's second law for the X and Y components, and we can solve that and determine the actual angle theta. So the summation of the forces in the X direction is equal to mass times acceleration in the X direction. Well, the acceleration in the X direction has to be the centripetal acceleration for it to maintain a circle. So that's going to be mv squared over r. The total forces are, as we can see, there's literally only one acting in the X direction. That's Fn sine theta. So Fn sine theta has got to equal m times v squared over r. That's going to be pointing in that way. That is a centripetal acceleration because it's center seeking, so the vehicle is turning like so. So we now have that. I'm going to label that equation 1. Now I take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now in this case, we're not imagining the car bouncing up and down like this, so there really should be no acceleration in the y direction at all. So I'll go ahead and eliminate that by saying it's going to be equal to 0. And then all the forces acting, even though it's not very well drawn to scale, is Fn cosine theta in the positive direction, and then mg in the negative direction. So I'll write minus mg, and that's all equal to 0. And this will be equation 2. From equation 2, I can see that Fn, the normal force, is going to equal mg over cosine of theta, and I'll call that 2 prime because it really just came from equation 2. Now I'm going to plug equation 2 prime into equation 1 so that I can solve for theta. So now equation 1 was Fn sine theta. I'm going to replace that with mg over cosine theta times the sine theta that was already there. That's going to equal mv squared over r. One thing you should be able to see is that immediately the masses on the two sides cancel out. So that's good because we don't have to do a different angle, whether it's a Mack truck or a Volkswagen Beetle or whatever. So it's independent of mass, in other words. The other thing we might see is that sine, this is really in the numerator, right? Because you're multiplying it by a fraction, so you can write it over 1. So I actually have mg times sine over cosine theta, but sine over cosine is just tangent. So I can ultimately write that g tangent theta is equal to v squared over r. Or finally, I get the result that theta is equal to the tangent inverse of v squared over gr. And that's the answer. That's the angle that we need. If you wanted to calculate the normal force, of course you could. It's not really necessary. But all you have to do now is take this tangent, put it in, this inverse tangent, put the angle that you get in here, and that would give you the normal force. But again, no one ever asks about that. It's really what's relevant is what is the angle of inclination. Now with this, you can do it for any particular velocity, any particular radius of curvature, and of course, any planet for that matter. So if you use g equals 9.8, that would obviously be probably you working on the Earth, but you could do other planets as well. I hope that helps. Have a good day.